Welcome to Group 1 of 1 ECEB, presenting the Standard Model, a journey into the building blocks of the universe. Brought to you by Lorenzo, Malana, Martinez, Palivino, Pamada, Pedong, Premian, Presbitero, Salva, and Segovia.
The Standard Model is a landmark in physics, explaining how particles like quarks, leptons, and bosons form everything around us. It unifies fundamental forces and led to key discoveries, like the Higgs boson, shaping our understanding of the universe with elegance and precision.
Background and context. What is the Standard Model? Standard Model explains particle interactions. Categorize fermions and bosons. Fermions, quarks, based on quantum field theory principles, and excludes gravity, dark matter, and energy. Origin of the Standard Model. From Thomson's electron discovery in 1897 to Rutherford's nucleus revelation in 1911, the 1930s to 50s laid quantum foundations. By the 1960s to 70s, the Standard Model unified particles and forces with other contributors.
Historical milestone. 1964 Higgs mechanism proposed particle gain mass. 1973 weak neutral currents confirmed. 1983 W&C boson discovered. 1995 top quark completed quark family. And 2012 Higgs boson confirmed the Standard Model.
Core concepts. Quarks form protons and neutrons, while leptons include electrons and neutrinos. Gauge bosons mediate forces, and the Higgs boson give particle mass. Quantum field theory unites quantum mechanics and relativity with symmetry guiding particle behavior. Fundamental forces. Fermions, like quarks and electrons, form matter. Quarks create protons and neutrons via strong force. Leptons, like electrons, interact through weak and electromagnetic forces. Bosons carry forces, and the Higgs boson give mass.
Core concept for fundamental forces. To make it short, electromagnetic force affects charged particles, govern electricity, magnetism, and light. Weak nuclear force causes radioactive decay and particle transformation. And strong nuclear force binds quarks into protons or neutrons and holds nuclei together.
So here in this slide, it explains the key theories and mechanism in the Standard Model, which QCD explains the strong force through quarks and gluons, the electroweak theories unifies weak and electromagnetic forces, and lastly, the Higgs mechanism shows how particles gain mass.
Core concepts, mathematical framework. Quantum field theory, where particles are filled with motion where quantum meets relativity. Gauge symmetry is invisible, rules the key, force is consistent. This is the backbone of the Standard Model.
This slide highlights key equations in the Standard Model, which the direct equation is for particle behavior, Coulomb's law for electromagnetic force, the Higgs mechanism is for mass, QZD for the strong force, and lastly, the Feynman diagrams for visualizing interaction.
The Standard Model explains a lot, but not everything. It can't explain gravity, dark matter, or dark energy. It also gets neutrinos wrong and doesn't tell us why matter is more than antimatter. Some parts feel like guesses, and it doesn't connect all forces. So it's useful, but not the full picture.
Now I would like to discuss to you its real-life applications. The Standard Model explains cosmic phenomena, organizes matter's particles, and inspires technological advances in electromagnetisms, driving innovations, medical imaging, wireless communication, data storage, and everyday automation. Fundamental forces, electromagnetisms, the weak and the strong nuclear forces. It organizes particles like quarks that make up matter. With tools like the Large Hadron Collider, scientists test predictions about the dark matter and supersymmetry, helping us understand the universe evolution since the Big Bang and driving breakthroughs in both science and technology.
The Standard Model helps create things we use every day. Motors and generators works because of its laws, powering machine and homes. It also explains how waves move, which helps us use phones, Wi-Fi, radio, and satellites. So even with problems, it's super helpful in real life.
These everyday technologies all harness electromagnetism. MRI machines uses magnetic fields to create detailed body scan. Hard disks drive store data by magnetizing small regions, and sensors and actuators convert electromagnetic signals into all motion or detection. All these everyday technologies, motors, phone, MRI machines, hard drives, and sensors work thanks to electromagnetism, one of the four fundamental forces described in the Standard Model, from converting motion into electricity to transmitting calls wirelessly to reading magnetic data.
Challenges and future aspects. The Standard Model has gaps. It excludes gravity, leaves dark matter and energy unexplained, and struggles with neutron oscillation, hierarchy issues, and lepton universality violations. Bridging this is the key to future discoveries. The search for new physics continues through experiments like LHCb and advanced colliders. Efforts to unify gravity and explore supersymmetry aim to solve key mysteries. Precision neutrino research, dark matter detection, and Higgs sector studies offer paths to expand the Standard Model.
The Standard Model explains fundamental particles and forces powering tech like MRIs, validated by the Higgs boson. It's still incomplete, missing gravity and dark matter. Future research aims to uncover deeper laws and a possible theory of everything.